Hello everyone, welcome to my channel Euclid Mathematics. Today I'm here with one of the important topic from group theory, which is a group and subgroup. In my today's video, I will explain to you all how to find subgroup of prime order group. In my previous video, I explained for finding subgroups of the prime element, which we can write multiple of two prime numbers like a p into q. Okay, so prime elements are the element we can write p into q. So I will explain some of the examples here from CSIR NET exam, and similar examples are in GATE exam also, SET exams also, because this topic is very much important. Okay, so here in my today's lecture I will explain this property here. Okay, in my previous lecture I explained same property and some examples. So if you wanted to check this property and examples, you can go through my previous lecture. I explained it in detail. Okay, now let's get started the property, and I will explain some of the examples from CSIR NET exam. Okay, so we have group, order of group is a p and q. Okay, and p and q both are prime. Okay, so order of group is a p into q and both are prime, and p strictly less q. Remember this one, p strictly less q. That means p is smaller than q and group G is a non-Abelian. If group G is a non-Abelian, then there exists, we have two possibilities, okay, of order p and order q. Okay, the number of subgroup of order p and number of subgroup of order q. Okay, so if order of G is a pq, it can divide Lagrange's theorem. We know that it has a divisor 1 pq and pq. Okay, so pq it is not possible because non-cyclic, non-Abelian. Okay, so left over here number of subgroup order p and number of subgroup of order q. Okay, in my previous example I explained number of subgroup of order p, which is a q. Okay, so number of subgroup of order p, which is a q, and number of subgroup of order q, which is only 1. Okay, so this is the property that we are going to apply in my further examples which asked in CSIR NET exam. Okay, that same property I explained in my previous videos. You can check it into my playlist, and if you have any doubt, comment me in a comment section. Okay, I will upload similar videos as per your difficulty and doubts. Okay, now see here my first example from CSIR NET, which is for 4.75 marks. Okay, multiple answer question, and question it is given: if order of G is a 39, then total number of subgroup in a G. Okay, so we have group of order is 39, and then we have to figure it out which one of the option is correct for subgroup of order G. Okay, so first option is 4, which is 16, which is a 2, and it is 1. Okay, so we have to check, and the question is for 4.75 marks. That means it has multiple answers. Okay, that might be one or more than one answers are true for order of G is a 39, and then subgroup is subgroup. Okay, so by using this property, we can easily say that the order of P is Q and order of Q is 1. Okay, and we know that identity and group G are always subgroup of group G. Okay, now let's go for the our solution of example. You can see it here. We have order of a G, one property from group theory. If group order of G is a P into Q and P strictly less Q, okay, then and P divides Q minus 1. Okay, then we can write group G is isomorphic to either ZPQ cyclic group, Abelian group, or it isomorphic to non-Abelian non-cyclic group. Okay, so here we have order of G is a 39. First of all, we have to find out where that group is isomorphic, what it contains element, which type of the elements are there. And once we come to understand the type of element, it is quite easy to figure it out, their subgroups. Okay, now let's go for its first G isomorphic to Z39. Okay, we have two possibility. Okay, we have two possibility, which is the first ZPQ and non-Abelian group. Okay, so we know that order of G 39, so I can write it into the multiple of 2, P multiplied by Q. So 3 multiplied by 31. Okay, similar like this property, 3 multiplied by 31, and 3 smaller than 13. Okay, so P strictly less Q, that means 3 smaller than 13, and P divides Q minus 1, so 3 divides 13 minus 1. Okay, and 3 divides 30 minus 1, it holds. 3 divides 4 or 12. Okay, so it gets 4. So we have two possibility of order of G39, which is one is a ZPQ, that means Z39. That ZPQ means Z3 into 13, which is a Z39, and another one is a non-Abelian group. Okay, so it is another one is non-Abelian group. So we have to find out subgroup of order 39 and non-Abelian group which exists there, what it is the order. Okay, so we know that number of subgroup of order Zn is a tau function. Okay, so tau function, it is a tau n is 39. Okay, so how to find tau n? Okay, I will explain how to find tau n here. So you can see it here. We want the value for tau 39. Okay, so tau 39 means we have to find the value for tau n. Tau n, for finding tau n, we use similar criteria for either 5 function. Okay, so 39 can be divided by 3. So 13 3s are 39, and we cannot find the divisor for 13. So 1 3 13s are 13. Okay, so we have to find out the value for E1, E2. E1 means the repetition of a 3, how many times are there? Okay, so if repetition is 2 times, then E1 is 2. But as we see here, it seems like the repetition of 3 is at only once, that means E1 is 1. Repetition of 13, it is also at once, so E2 is also 1. Okay, so E1 1, E2 1. So repetition for these two elements is only one time. Okay, and tau n, it says that the repetition of first element plus 1 multiplied by repetition of a second element plus 1 plus repetition of a n element plus 1. Okay, so this is the way we can find tau n. Okay, now let's find out tau 39. So tau 39, it says that, so tau 39 I written as a E1 plus 1, E2 plus 1. Why two multiples? Because we got the repetition only one time. Okay, for 3 and 13. So if you have one another element, you get the here E3 plus 1. Okay, so I have two elements here. So E1 plus 1 is a 1 plus 1. E2 plus 1 is also 1 plus 1. Okay, so E1 it is here and E2 it is here. Okay, so tau 39 it comes 4. Okay, it's easier to find out tau 39. So let's get back to the example. So here, if we have G isomorphic to Z39, that means number of a G is a tau n. Okay, tau 39, which is a 4. Okay, now next possibility it is here, if a G isomorphic to non-Abelian group. What happen if group is isomorphic to non-Abelian group? Okay, so we saw above here property that you can see order of a G is a PQ and a P strictly less Q and G non-Abelian. Okay, so we have other property that G is non-Abelian. It has a two possibility, which first is a subgroup of order P is Q. Okay, so 13 P value for P and Q. What is the value for P and Q in our example? 3 and 13. Okay, and 3 smaller than 13. So value for P is a 3 and Q is a 13. So 3 smaller than 13. So that means subgroup of order 3 is a 13. Okay, subgroup of order 3 is 13 and subgroup of order 13 is 1. Okay, so we got the two subgroup whose first subgroup order 3 is a 13 and subgroup of order Q is 1. Okay, so you can see it here. Subgroup of order 3. Okay, subgroup of order 3 which is 13 and subgroup of order Q each is 1. Okay, these are the two subgroup. I found it here for our non-Abelian group. Okay, that means first subgroup of order 3 is 13 and subgroup of order Q is 1 by using our property. But it's not finished yet, because we know that identity is also element there whose order 1 and group G, it is also subgroup of group G, because the property for subgroup, it says identity and group G both are subgroup of G. So identity element whose order 1 and subgroup G is a group, okay, which is also subgroup whose order 1 also. Okay, that means not order 1, the group we have to count it as 1. Okay, so identity 1 and group it is also 1 and Q is also 1 and P is 13. Okay, so G is a non-Abelian, then number of subgroup, which is a addition for all these, which is a 16. Okay, so now let's verify which one of the option is correct between our 4 options. Okay, so I found it here. When group is a cyclic, which is isomorphic to Z39, it has a subgroup 4 subgroup. Okay, tau 39 is a 4. And next, when group is a non-Abelian, okay, then we say that that group which has all subgroup, total G is a non-Abelian, then subgroup which is the 16. Okay, so 2 is not possible, 4 is not possible. I hope so you all have understood my example, which based on this property. Okay, which asked in CSIR NET exam, and similarly same question get asked for the GATE exam also, SET exam and different competitive exams also. Okay, so I hope so you all have understood my today's lecture. So if you wanted to see more videos similar like this, you can check it into my playlist. If you have any doubt, you can ask me in the comment section. So thank you everyone. Thank you for my today's lecture.